Now, you know that in the previous two videos of Unit 6, that is Water Technology, first of all we discuss all the introduction about the unit, and then secondly we discuss the one of the property of the water by which we are able to determine the quality of the water, that is the pH of the water. So now the next property of the water is the hardness and the alkalinity of the water, by which again we are able to determine the quality of the water or the level of the impurities which are present in the water in order to treat it or in order to convert the wastewater into the pure water. It means you know that if the pH of the water is neutral, then it is of the good quality. While if the pH of the water or any aqueous solution is below 7, then it is acidic in nature, and if it is above 7, then it is basic in nature. And again you know that in case of the drinking water, we always require the neutral water. If it is acidic or basic, then it is very harmful for the health, and that's why by determining the pH of any aqueous solution or of water, we are able to treat it or convert it into the pure water or the water quality which we require. So in the same way, the hardness is one of the property of water by which we are able to determine the concentration of the impurities in water in terms of the calcium and magnesium ions. These ions convert the soft water into the hard water. Now, one thing you know that the various types of the impurities which are present in the natural water impart or change some of the properties or the characteristics of the water. So, from the point of view of industrial use, the characteristics and the effects of these impurities on the water quality generally include the color of the water, then the taste of the water, then odor, turbidity, then sediments, microorganisms, the dissolved gases, silica content, and finally the dissolved mineral matter, which includes the hardness, alkalinity, the total solids, and the corrosion. So you know that basically we determine the corrosive property of the water by the help of the pH of the water, because you know that more acidic is the water, more corrosiveness it contains. Now, in general, for the industrial use, we generally determine the presence of the calcium, magnesium, sodium, potassium, bicarbonates, carbonates, hydroxides, chloride, sulfate, nitrate, fluoride, silica, iron, manganese, and the mineral acids. Now, the most important quality of the dissolved mineral matter from the point of view of industrial application includes the hardness and the alkalinity. It means by the help of these two properties of the water, we are able to determine the most of the impurities which are present in the water in order to use in the industry for the different applications. It means in this unit we are discussing the three properties of the water which are changing due to the presence of the impurities. The first one is the pH of the water that we have already discussed. The second one is the hardness of the water, and the third one is the alkalinity of the water. So first of all, what is hardness? So hardness is can be defined as the soap consuming capacity of the water sample or the property of the water due to which it does not form the leather easily with the soap. It means you know that whenever you mix the natural water without any impurity with the soap, then of course it will form the leather with the soap very easily. But when such water contains the impurities in the form of calcium and magnesium ions, and when such water is mixed with the soap, then it does not form the leather with the soap, and that's why such kind of the hardness causing impurities causes the hardness of the water. It means Such kind of the calcium and magnesium ions or other ions have the soap consuming capacity. It means you know that soap generally consists of the sodium salts of long chain fatty acids such as the oleic acid or the palmitic acid or stearic acid. So these ions react with the sodium salts of the long chain fatty acids which are present in the soap to form the insoluble scums of the calcium and the magnesium soaps which do not possess any detergent value or cleaning tendency. It means such kind of the calcium and the magnesium ions or the other kinds of the ions which are present in the water have the soap consuming capacity. It means you know that the soap generally consists of the sodium salts of the long chain fatty acids such as the oleic acid or the palmitic acid or the stearic acid. So when we mix such kind of the soap with the water which contains the calcium or the magnesium ions, then this ions reacts with the sodium salts of the long chain fatty acids which are present in the soap to form the insoluble scums of the calcium and the magnesium which do not possess any detergent value. For example, when we wash our hands with the borewell water by using the soap, then you observe one thing that such kind of the water do not possess much more quantity of the leather. So it is because in such kind of the borewell water, there are the impurities are present in the form of calcium and magnesium ions which again consumes the soap and that's why it forms the insoluble scums of the calcium and the magnesium which do not have any detergent value or cleaning tendency. So this is the hardness of the water which is generally caused by the calcium or the magnesium or other hardness causing ions. Then the other metal ions like the iron, manganese, aluminium also reacts with the soap in the same fashion and that's why contributes to the hardness of the water, but generally such kind of the metal ions are present in the natural water only in trace amount. Further, the other acids such as the carbonic acid can also cause the free fatty acids to separate from the soap and that's why contributes to the hardness again. However, in practice, we generally consider the hardness of the water sample as a measure of its calcium and the magnesium ion content. It means in general, we consider the hardness in terms of the calcium and the magnesium ions impurities. Now, one thing you know that the hardness is caused by the soluble salts of calcium, magnesium or other ions like the iron, manganese, sodium, chlorides, nitrates or etc. Now, one important thing is that the degree of the hardness of water is generally depends upon the type of the impurities which are present in the water and the amount of the impurities which are present in the water. So, depending upon the action of the soap on the water, there are the two kinds of the water are present. The first one is the soft water and the second one is the hard water. So, first of all, the water which produces the leather readily with the soap solution is called as the soft water and it is because of the absence of the calcium and the magnesium salts in the water. It means the water that is not hard, that is does not contain the mineral salts that interfere with the formation of the leather with the soap and such kind of the water is the soft water. Oppositely, when the water contains the impurities in the form of salts or the ions like the calcium or the magnesium ions, and when we mix such kind of the water with the soap, then it does not form the leather while it produces the white precipitate or the scum and such kind of the water is the hard water. So you are observing here in this reaction when you mixed the hard water, that is the water which contains the calcium and the magnesium ions with the soap, then it produces the soap solution along with the precipitate or the scum, that is the sticky pipette. So in the previous slide, we discussed the type of the water, that is the hard water and the soft water, depending upon the impurities, that is the calcium and the magnesium ions in the water. Now, when the water is hard, then again there are the two types of the hard water, or there are the two types of the hardness, depending upon the types of dissolved salts present in the water. The first one is the temporary hardness and the second one is the permanent hardness. So first of all, the temporary hardness is due to the presence of dissolved bicarbonates and the carbonates of the calcium and the magnesium ions, or due to the carbonates of the iron or other ions. It means the name indicates the temporary hardness can be removed easily by the process of boiling of water. It means when the water contains the hardness in the form of dissolved bicarbonates of the calcium and the magnesium ions, then such kind of the hardness of the water can be removed by the boiling of the water. So in this process, due to the heating, the soluble bicarbonates are converted into the insoluble carbonates or the hydroxides, and that's why the water is then converted into the soft water, that is without any calcium and the magnesium ion. For example, you are observing here in this reaction, when the water contains the calcium bicarbonate and when we heat such kind of the water, then it is forming the insoluble calcium carbonate, which we easily remove from the water with the formation of water and CO2. It means the boiling process promotes the formation of the carbonates which are insoluble from the bicarbonates, and that's why precipitates the calcium carbonates out of the solution of water, and that's why leaves the water which is softer in nature, that is the soft water. In short, the temporary hardness is due to the presence of the dissolved bicarbonates of the calcium and magnesium ions, and when we boil such kind of the water, then this bicarbonates of the calcium and magnesium ions are converted into the insoluble carbonates of the calcium and magnesium ions, and that's why we are easily remove such insoluble ppt from the water, and so the water is converted into the soft water. Now, the second type of the hardness is the permanent hardness. So, such kind of the permanent hardness of water is caused by the soluble salts of the calcium and the magnesium ions other than the carbonates and the bicarbonate. It means when the water contains the impurity other than carbonate or bicarbonate, then it will cause the permanent hardness in the water, which is not removed by the boiling. It means you know that when the water contains the impurity in the form of bicarbonates of calcium and magnesium ion, then such kind of the impurities can be easily removed by boiling, because after boiling you know that this soluble bicarbonates of calcium and magnesium ions are converted into the insoluble carbonates of calcium and magnesium ions, and that's why the hard water is converted into the soft water. However, in case of the soluble salts of calcium and magnesium ions other than the carbonates and the bicarbonates, like the calcium chloride or the magnesium sulfate or magnesium chloride, then such kinds of the impurities on boiling are not converted into the insoluble ppt, or rather they are converted into the more soluble impurities as the temperature rises, and that's why on boiling such kind of the permanent hardness cannot be removed from the water. So one thing you know that by just boiling we are not able to remove the permanent hardness from the water. However, it can be removed by the other methods like the lime soda process or the zeolite process, which completely removes the soluble salts of calcium and magnesium ions other than the carbonates and the bicarbonates which are present in the water, and that's why we are able to convert this permanent hardness into the soft water that is free from any kind of the calcium or magnesium ion impurity. So one thing you understand that what is temporary hardness and what is permanent hardness. So now the total hardness is the sum of this temporary and the permanent hardness. Now basically, what are the causes of this hardness in the water? So you know that it is maybe due to the dissolution of the minerals. It means when the rainwater flows or deposits on the ground or percolates deep down through the earth crust, then it comes in contact with the salts which are present in the earth crust, and that's why the water soluble salts of heavy metals give the hardness to the water. Then again you know that when the rainwater drops come in contact with the carbon dioxide in the atmosphere, then during their path towards the earth's surface, this CO2 is a water soluble gas which react with the water. Then such CO2 dissolved water when comes in contact with the CaCO3 or the MgCO3 containing the rocks like the limestone, then these insoluble minerals are slowly converts into the soluble and the hardness causing bicarbonates, and that's why convert the soft water into the hard water. Now, the important thing is that how we will determine the concentration of the hardness which is present in the water. So basically, the concentration of the hardness producing salts are usually expressed in terms of the equivalent amount of calcium carbonate. Now, the important thing is that why we are taking the concentration of the hardness producing impurities in terms of equivalent amount of calcium carbonate. So, the reason is that basically you know that the molecular weight of the calcium carbonate is 100, and that's why the equivalent weight of the calcium carbonate is 50, that is the whole number. So that's why the calculation in the water analysis can be very easily we are able to simplify. Then the second reason is that you know that the calcium carbonate is one of the most insoluble salt that can be easily precipitated in water treatment, and that's why we generally take the concentration of the hardness producing impurities in terms of the equivalent amount of calcium carbonate. So now there is one formula in order to determine the amount of the hardness producing impurity in terms of the equivalent amount of the calcium carbonate, and this formula is X, that is the weight of the hardness producing substance into 100 divided by the molecular weight of the hardness producing salt or impurity. For example, if you have to determine the concentration of the hardness causing impurity, that is the calcium sulfate CaSO4, in terms of the equivalent weight of the calcium carbonate, then you know the formula. So in that formula you know that first of all the molecular weight of the calcium carbonate is 100. Then you know that the concentration of the impurity is given in the question, that is 43 milligrams per liter, divided by you know that the molar mass of the impurity, that is the molecular weight of the impurity, is 136, and that's why by calculation we are able to determine the concentration of the impurity in terms of the calcium carbonate equivalent. Now, one very important thing in order to solve the numericals of the hardness, always remember there are the certain substances which do not contribute towards the hardness, and we have to ignore such kind of the impurities if they are given in the question. So, such kind of the hardness causing impurities are the KCl, NaCl, SiO2, then Na2SO4, Fe2O3, and lastly K2SO4. It means if such impurities are given in the question, then we have to ignore it because these substances do not contribute to the hardness of the water. It means they do not cause the hardness of the water. So one thing you always remember that all the carbonates and bicarbonates of calcium and magnesium are taken as the temporary hardness, and all the chlorides, sulfates and nitrates of calcium and magnesium are taken as the permanent hardness. Now see one numerical, that is calculate the temporary, permanent and the total hardness of the sample of water containing MgHCO3 twice 7.3 milligrams per liter, CaHCO3 twice 16.2 milligrams per liter, magnesium chloride 9.5 milligrams per liter, CaSO4 13.6 milligrams per liter, SiO2 10 milligrams per liter and sodium chloride 7 milligrams per liter. So first of all, we have to write all the impurities which are given in the question in one of the column. Then you know that again the concentrations in milligrams per liter are given. Then you know that we always determine this concentration in terms of the calcium carbonate equivalent. So you know the formula also. So by using that formula, we will determine the concentration in terms of the calcium carbonate equivalent. Example, for the first impurity, that is MgHCO3 twice, you know the molecular weight of calcium carbonate, that is 100. Then again you know that in the ratio the molecular weight of MgHCO3 twice is 146. Then you know into the concentration of impurities given in the question, that is 7.3. So that's why the answer is, or the calcium carbonate equivalent is 5. So in the same way we will determine for all the other impurities. Now you know that in the question we have to determine the temporary, permanent and total hardness. So one thing you know that the temporary hardness is due to the carbonates and the bicarbonates of the calcium and magnesium, and other than the carbonates and the bicarbonates of calcium and magnesium, all the impurity contributes towards the permanent hardness. So that's why in the question you are observing the temporary hardness is due to the magnesium bicarbonate and the calcium bicarbonate. So that's why we will determine the temporary hardness by adding the concentration of the magnesium bicarbonate and the calcium bicarbonate, that is the 5 plus 10, which is equals to 15 milligrams per liter. Then again you know that the permanent hardness is due to the all other impurities other than the carbonates and the bicarbonates. So you are observing in the column it is due to the magnesium chloride and the calcium sulfate, that is the CaSO4, and that's why in terms of the calcium carbonate equivalent the addition is of the 10 plus 10, that is the CaCO3 equivalent for the magnesium chloride is also 10 and for CaSO4 is also 10. So that's why the sum is 20 milligrams per liter. Now you know that we discussed previously also that the total hardness is the sum of the temporary hardness and the permanent hardness, and that's why it is the sum of 15 plus 20. So it is 35 milligrams per liter, that is the total hardness which is present in the water. So you know that till now we discussed the two properties of the water which are generally changed due to the presence of the impurities. The first one is the pH of the water, and the second characteristic of the water is the hardness of the water. So now the third one is the alkalinity of the water, by which again we are able to determine the level of the impurities which are present in the water. Now, one thing you know that as we discussed in the previous topic of pH of water also, that basically the alkalinity of water is due to the increase in concentration of the OH minus ions. So that's why the alkalinity of water means the total content of those substances in water that cause an increase in concentration of the OH minus ions upon dissociation or due to the hydrolysis. It means those impurities in water which increases the concentration of the OH minus ions due to the dissociation or due to the hydrolysis, then it causes the alkalinity of the water. So basically, this alkalinity of the natural water is generally due to the presence in them of the HCO3 minus or SiO3 2 minus or HiSCO3 minus, and sometimes also due to the CO3 2 minus ions. So there are the various kinds of impurities are present in the water which causes the alkalinity of the water, that is the increase in the concentration of the OH minus ions. Now, depending upon the anions which are present in the water or responsible for the alkalinity of the water, there are the three types of the alkalinity, or the alkalinity is classified as the bicarbonate alkalinity, that is due to HCO3 minus ions, then the carbonate alkalinity due to the CO3 2 minus ion, and the hydroxide alkalinity, that is due to the OH minus ions. Now, the important thing is that basically the highly alkaline water causes the caustic embrittlement. So now what is caustic embrittlement? So it is the phenomena during which the boiler material becomes brittle, or any metal becomes brittle due to the accumulation of the caustic substances, and that's why it is one of the fast type of the boiler corrosion which is caused by the highly alkaline condition of the water. So we will discuss this topic of the caustic embrittlement in detail in the later topic. Then again, this highly alkaline water causes the deposition of the precipitate and the sludge in the boiler tubes or the metal pipes. So these are the some of the effects of the highly alkaline water. Now, with respect to the constituents which causes the alkalinity in natural water, the following situations may arise. It means the alkalinity is maybe due to the hydroxides ions only, it may be due to the carbonate ions only, and may be due to the bicarbonate ions only. Then again, it may be present in combination of the hydroxides and carbonates, or carbonates and bicarbonates. Now here, one situation we skip, that is the possibility of the hydroxides and the bicarbonates. So it is because when the hydroxides and the bicarbonates combine with each other, then they only form the carbonates with the formation of the water. Now, the important thing is that how you will determine the type and the extent of the alkalinity which is present in the water sample. So, it is by the help of titration. So, first of all, in this titration, you have to take the water sample of particular amount, for example, 50 ml or 100 ml in the conical flask, and then you have to add the phenolphthalein indicator to it. So, it will give the pink color. Then you have to titrate it against the standard acid like the H2SO4 which is present in the burette. So you know that we are adding the acid from the burette to the conical flask, and that's why the color is changes from pink color to the colorless. Then we will add the another indicator, that is the methyl orange indicator, to the same conical flask, and we will do the titration continue from the same burette. So after adding the methyl orange indicator, the color is changes from colorless to yellow, and then after the titration, we will record the end point when the color is changes from yellow to red. So now the total amount of the acid that we used from the beginning of the experiment, that is from the phenolphthalein indicator to the methyl orange indicator, corresponds to the alkalinity which is present in the water sample. Now after this titrations, there are the further calculations also in order to determine which type of the alkalinity is present in the water and in which amount or what is the extent of this alkalinity in that given water sample. Now This is one of the table by which we are able to first of all determine the type of the alkalinity which is present in the water, that is whether it is due to the hydroxide, due to the carbonate or due to the bicarbonate ion, and then secondly after determining the type of alkalinity by using the formulas which are given in the table, again we are able to determine the extent of the alkalinity which is present in the water sample. Now first of all, see this formula. You know that we discussed in case of the hardness also the concentration in terms of CaCO3 equivalent. So in the same way the alkalinity is also generally expressed as parts per million, that is ppm, in terms of the CaCO3 equivalent. So the alkalinity is determined by the formula, that is the volume of the N by 50 acid that we are taking in the burette into 1000 divided by the volume of the sample which we are taking for the titration. So the answer is in ppm or milligrams per liter. For example, see one numerical. If 100 ml of the raw water sample on titration with N by 50 H2SO4 required 12.4 ml of the acid to the phenolphthalein endpoint and 15.2 ml of the acid to the methyl orange endpoint, then determine the type and the extent of the alkalinity present in the water sample. Now, in the question, you are observing one thing, that the phenolphthalein endpoint, that is P is equals to 12.4 ml, and M, that is the methyl orange endpoint, is given in the question, that is 15.2 ml. Now, look on the table that we discussed in the previous slide. So, you observe one thing, that the relationship between the phenolphthalein and the methyl orange endpoint is P greater than 1 by 2 of the methyl orange endpoint, that is M. It means initially always, first of all by observing the endpoints of the phenolphthalein and the methyl orange endpoint, first of all we have to relate the relationship between these two readings by observing the column. Now, by the column, once you know the relationship between the phenolphthalein endpoint and the methyl orange endpoint, again you are able to know the type of the alkalinity. For example, in this case, you know that the relationship is P, which is greater than half of M, and that's why by the help of column you know that the alkalinity is only due to the OH minus ion and CO3 2 minus ion, that is hydroxide, and the carbonate ion, and not due to the bicarbonate ion. Now again, by the help of the formula which are given in the table related to the OH minus ion and CO3 2 minus ion, we are able to determine the volume of the N by 50 H2SO4 that we are taking in the burette equivalent to the OH minus ion present in the 100 ml of the water sample, and individually equivalent to the CO3 2 minus ion present in the 100 ml of the water sample. It means, see, the volume of the N by 50 H2SO4 equivalent to the OH minus ions present in the 100 ml of the water sample is determined by the formula that is given in the column, that is 2P minus M. So just put up the readings directly in this formula. For example, you know that 2 is as it is, then the phenolphthalein endpoint is 12.4 and minus the methyl orange endpoint which is given in the question is 15.2, and that's why the answer is 9.6 ml. Now similarly the formula is given, that is 2m minus p, in order to determine the volume of the N by 50 H2SO4 equivalent to the CO3 2 minus ion present in the 100 ml of the water sample, and that's why the answer is 5.6 ml. Now, the formula of alkalinity, you know, it is the ratio of volume of N by 50 acid into 1000 divided by the volume of sample taken for the titration. So, now finally, in order to determine the extent of the alkalinity due to the OH minus ion and CO3 2 minus ion, we will put all the readings in this formula. So see, in order to determine the extent of alkalinity due to the OH minus ion, first of all we put all the readings in this formula. That is, you know that the volume of N by 50 acid for the OH minus ion, as we discussed or determined previously, is 9.6 ml. Then you know that in the formula the 1000 is as it is, then divided by the volume of sample taken for the titration. So you know that we take 100 ml of the water sample, and that's why after calculation the answer is 96 milligrams per liter in terms of the CaCO3 equivalent. So that is the alkalinity of the water sample due to the OH minus ion is 96 ppm. Now similarly, in case of the alkalinity due to the CO3 2 minus ion, again you know that the volume of N by 50 acid for the CO3 2 minus ion, as we determine, is 5.6 ml in 2000 is as it is, divided by, you know that the volume of the water sample taken for the titration is 100 ml, and that's why the answer is 56 milligrams per liter. So, the extent of the alkalinity in the water sample due to the CO3 2 minus ion, that is the carbonate, is the 56 ppm. So, in this way, by the help of just one column, we are able to determine the type of alkalinity also, and by using the formula, we are able to determine the extent of the alkalinity also, which is present in the water sample.